Good morning. Welcome to the lecture series on digital electronics 18 EC 302C. In today's lecture, we'll look at how to represent boolean functions or logical functions in standard forms. So, we know that all logical functions are generally expressed in terms of various combinations of the logic variables on which the function depends. And when we are representing by the various combinations of the variables, in all those combinations, the logic variables may be present either in true form or in its complement form. For example, if a logical function depends on, say, the variable a, so then a can be present in one combination as in its true form, and in other combination maybe it is present in its complement form, that is a bar. So we'll look at how to represent, or what are the various ways to represent the boolean or logical functions in a standard way. So any logic function can be expressed in the following forms, and they are sum of the products form, it is in short called as SOP form, stands for sum of the products. And the logic function can also be expressed in the product of sums form, or it is called in short POS form. So before going to see how to represent the logic functions in these forms, we'll look at what is meant by product of the boolean variables and what is meant by sum term in the boolean algebra. Then we'll define, then we'll look at how to represent, or which representation is called SOP representation and which type of representation is called POC representation for boolean functions. So first we'll look at what is meant by product term. So product term is the logical product of several variables on which a function depends. So for example, that means, for example, if a function depends on three variables, the logical product of the variables, the three variables, or any of the three variables, is called a product term. So logical product means an AND operation performed between any of the three variables. That means at least two variables must be present to perform AND operation. So in that product term, to get the product term, you can perform AND operation between any of the two variables, or you can perform AND operation on the three variables on which the function depends to get a product term. So for example, and one more thing you have to notice, that in the logical product of the several variables on which the function depends, the variable can be in either form. That means it can be present in its true form or in its complement form. That means the function depends on the variable, say b, then in that particular product term, the b can be either present in its true form as simply b, or it can also present in its complemented form as b complement. So if I, as for example, if I assume that a function depends on three variables, then I can say that the logical product of the three variables A, B bar, C, the logical product of the three variables, where the variables may present either in original form or in its complement form, is called as a product term. Is called a product term. And here you can see this is one product term, and here you can see that A and C are present in original form, but B is present in its complemented form. Right? So simply the product term is a logical product of any number of variables on which a function depends. And similarly, we have one more term to define. It is called as sum term. So sum term is similarly the logical sum of the several variables on which a function depends. So here also the variables on which the function depends are logically summed. That means an OR operation is performed between any of the variables on which function, any number of the variables on which a function depends. And here also the variable can be present in its either in its true form or in its complemented form. So if I assume that a function f depends on the three variables a, b, c, then I can say that a plus c bar is sum term for the function. And here you can see that though the function depends on three variables, the sum term may contain all the three variables, or it may contain less number of variables. So here only the two variables are there on which our operation is performed, and we obtain a sum term. And in this you can see that A is present in its original form and C is present in its complement form. So this is how we form sum terms. Next, then what is sum of products? So here we have seen that any logic function can be expressed in two different forms, either in sum of the products forms or product of sums form. So then what is sum of the product form? Sum of the product, that means it's a logical sum of two or more product terms. What is a product term? We defined here. So that means if you take a logical sum of two or more product terms on which the function depends, it is called as sum of products forms. That means we will take product terms on which function depends and will perform OR operation on the product terms. So then that expression is called as sum of product form for the logic function. So for example, I can write the expression for the function y, which depends on the three variables a, b, c. Then the sum of product form for the logical function can be in this ab plus bc plus c bar a. So here the function depends on the three products A, B, B, C and C bar A, and we have taken a logical sum of the three products, and that expression is called as sum of products expression. And similarly, we have the product of the sums. So product of sums form for a logic function is the logical product of two or more sum terms. What is sum term? We already defined here. Sum term is the logical sum of any number of variables on which the function depends. And if we take such sum terms and if we perform AND operation on all those sum terms, then we'll get the product of sums form of representation for the logical function. So for an example function y, which depends on the three variables a, b, c, the product of sums expression can be a plus b plus c bar dot a plus b bar. So here you can see that this is one sum term which contains all the three variables, and this is the second sum term which contains only two variables out of the three on which function depends. And we have taken these two sum terms and we have performed a logical product operation on these two sum terms. So the expression that we get by performing logical product on these two sum terms is the product of sums form for the logical function y. So if we express any logic function either in sum of product form or in product of sums form, then it is called as standard form, or it is called standard representation for logical functions. But we cannot assume that all functions are always represented in the standard form, that is either in SOP form or in POS form. Some of the functions may be represented in non-standard forms. So non-standard, so this also we have to see what is in my non-standard form. That means the logic function is not present either in SOP form or in POS form. That means it will not contain sum of the products completely, or may not contain product of sums completely, but it may contain the mix of the two, and that is called as non-standard form. So if we take an example, then f function, when it is expressed as ab plus cd and a bar b bar plus c bar d bar, and here you can see that there are some terms, right? There are some terms, and here you can see that there are also product terms. So this is sum of products, this is also sum of two products, sum of two products, sum of two products, and these two sum of products are again multiplied or logically ANDed. So this is a non-standard form. So how to get a standard form? Then you have to use the boolean multiplication, or you have to use the boolean postulates, that is AND operation over or operation over AND. Then you will get the function in either in SOP form or POS form. So this is not the important representation for the boolean function. So we always try to represent any of the function in either SOP form or in POS form. So next we look at what is meant by standard product. So before that, we defined what is meant by product term. Now we want to define what is meant by standard product term. So when we are defining product term, we said that it is a term obtained by performing AND operation on any number of variables on which the function depends. That means if function depends on 3 variables, the product term may contain either all the 3 variables, or it may contain 2 variables. That means it may contain any number of variables. That means each product term may not be required to contain all the variables on which the function depends. So that is called as product term. So now we are defining one more product term, that is called as standard product term, or it is also called as min term. So then what is in my standard product and how it is different from a normal product term? So a product term containing all n variables of the function in either true or complemented form is called as standard product. That means here it is also a product term. That means it is also a term obtained by performing AND operation between all the variables on which the function depends. That means if a function depends on, say, 4 variables, a function depends on 4 variables, and the product term must contain all the 4 variables, either in true form or in complemented form. Then that product term is called as standard product term or min term of the function. So here you can see that for a 2 variable function, so for a 2 variable function, if I assume that the variables are a comma b, so for a 2 variable function, if I assume that the variables are a comma b, then the possible combinations of the product terms which contains all the 2 variables are a bar, b bar, and a bar, b, and ab bar, and ab. So when you take a function of two variables, say a and b, then these are all the possible product terms which contains all the variables on which the function depends. So they are a bar, b bar, and a bar b, and ab bar and ab. So I can say that for the function which depends on two variables, we have four standard products, and we have four minterms, and these are also called as fundamental products, or you can call them as standard products, or you can call them as minterms. And here you can see that in each term a variable is written in its original form if its value is 0. That means here you can see that here in the first term it is a bar dot b bar. That means here in the term the value of a is 0, so it is written as a bar, and here the value of b is 0, so it is written as b bar. And similarly, the last minterm, the variable value is 1, so it is written in its original form, and the variable value b is also 1, so it is also written in its original form. So in minterms or in the standard products, a variable is written in general in its original form if its value is 1, and the variable is written in its complemented form if its value is 0. And you can see that, so for two variable function we have four minterms, and if you take a three variable function, then you will be having 8 minterms. And how to obtain those minterms? So that we will write here a, b, c, and we will list out all possible combinations for the three variables. So all the three variables can have value of 0, and the three variables can have 0, 0, 1, and 0, 1, 0, 0, 1, 1, and 1, 0, 0, and 1, 0, 1, 1, 1, 0, 1, 1, 1. So here you can see that these are all the possible combinations for the inputs, and you can see that, so since we have 8 possible combinations for the input variables, when there are 3 variables we will have 8 possible combinations, and that means we can write 8 different AND terms, or we can write 8 different product terms or standard products, or we can write 8 minterms. And how to write minterms for each of these combination? So when a particular variable assumes a value 0, then in the minterm it should be written in its complement form. So here a assumes 0, so a must be written as a bar. B assumes 0, so it must be written as b bar, and C assumes 0, it must be written as C bar. So this is a minterm corresponding to the input combination of inputs a equal to 0, b equal to 0, and C equal to 0. Similarly, we can write one more minterm corresponding to this set of values for the input variables: a equal to 0, b equal to 0, c equal to 1. So a and b must be in complemented form and C must be in original form. So this way we can write minterms. So A0, B1, C equal to 1. So the minterm is A bar, B, C bar here, and here the minterm is A bar, B, C, and here it is A, B bar, C bar, and here it is A, B bar, C, and here it is A, B, C bar, and here it is A, B, C. So it is ABC means A dot B dot C. Logical multiplication operation is performed between the three variables. And how the variables are taken? The variable present in its original form, if its value is 1. The variable present in its complement form, if its value is 0. So this way, so for a 3 variable function, since there are 3 variables, we got 8 minterms or 8 standard products. So since 2 power 3 is 8, we'll get 8 standard products. So for an n variable function, the number of standard products or number of minterms will be 2 power n, where in each minterm or in each standard product, the variable is present in its original form if its value is 1, and the variable is present in its complement form if its value is 0. So then we have, when we know the standard products are minterms for a particular function, then we have one more way of representing the logical functions, that is standard sum of products. Standard sum of products. So it is not simply SOP, but it is standard sum of products, or it is also called canonical sum of products form. So standard sum of products. So then what is meant by standard sum of products? So when a boolean function is expressed as the logical sum of the minterms, right? So when a boolean function is expressed as logical sum of not product terms but logical sum of standard products, or logical sum of the minterms, which minterms for which the value of the function is 1. So right, so when a function is expressed as sum of the minterms, not all the minterms of the function, but only those minterms for which the value of the function is 1. Such minterms, if they are taken and a sum operation is performed, logical sum operation is performed on those minterms, then we will get the expression in the form of standard sum of products. So here, if I assume that there is a function f and which has minterms, say a bar bc and ab c bar and a b bar c, for which the function becomes 1, then the function f of a comma b comma c. So here this way we will write, and this is a function which depends on the 3 variables a comma b comma c. Now this function can be expressed as sum of the minterms for which the function, the value of the function is 1. So here assume that, so these are the minterms for which the value of function is 1. So then I can sum these minterms, and this expression for the function is called as standard sum of products. And I can, when a function is expressed in standard sum of products, that means sum of minterms, I can also say that this is sum of minterms, then I can give a short representation for this expression. Since all these are the minterms which are summed, then I can represent the minterm with small letter m. Small letter m stands for a general minterm. So then to specify to differentiate between the minterms, I will use a subscript for a particular minterm, which is the decimal equivalent of the binary value of the minterm. So here it is a bar bc, that means, so this is a bar means it is 0, its value is 0, bc means its value is 1 1. So here the bits are 0 1 1, and so this is a binary 0 1 1. So when it is expressed as decimal, it becomes 3. So this minterm I can write it as m3. So since these are all the minterms, I use the small letter m, and the subscript will be the decimal equivalent of the binary number which is represented by the minterm. So this I can write it as m5 as it is 1 0 1. This is m6 1 1 0. So in short, I can write this expression as m3 plus m5 plus m6. Simply I can write this as summation of m3 5 6. The sum of minterms 3 5 6. So this is how any boolean function can be expressed as the logical sum of the minterms. This logical sum of minterms is also called as standard sum of products. So similarly, for example, if a function may not be in standard sum of product form, that means each product term may not contain all the variables, and each product term may not be a minterm. So then in that case, how to convert any logic function into a standard sum of products form? So for that, what we have to do is check each term of the logic function and keep the term as is if it's a minterm. That means if it contains all the variables on which the function depends, either in its true form or its original form. But if a particular term missing a variable, say x, then multiply the term with x plus x bar, and after multiplying the terms, then if there are any duplicate terms, remove the terms. So then that will give you the expression in standard sum of products. So we'll look at an example which shows how to convert or how to obtain standard sum of products expression from the given expression of the function. So here example shows obtain the standard sum of product form. So obtain the standard sum of product form for the following function, and the function given to us is f of ab equals a plus b. So this is the function given to us, and you can see that here the function contains two terms a and b, and these two terms are summed. So this is a sum of product terms but not standard sum of product terms. As you can see, the first term, product term, contains only one variable on which function depends. It doesn't contain the two variables on which the function depends. So here you can see that. So what you have to do, so you are observing all the product terms, and in the first product term, what is a missing variable? So the function depends on two variables, but here a is present but b variable is missing, either in its original form or complement form. So what you have to do, so for this product term, you perform or you multiply this product term with the missing variable summed with its complement or odd with its complement, that is a dot b plus b bar. Next you take this or as this, and the next product is b, and here also you can see that it is missing, this product term is missing a variable. So what you have to do, you have to multiply this with the variable summed with its complement a plus b bar. Then we use the theorems of the Boolean algebra. So this can be written as ab plus ab bar plus ab plus a bar b, and here you can see that this is a redundant term or repeated term. So since a plus a equal to a only, so you can neglect one, and you can write this as is ab plus ab bar plus a bar b, and this is the function f, and here you can see that now the function is expressed in the form of standard sum of products or sum of min terms. As you can see, each product term contains all the variables on which the function depends, and those variables either present in original form or their complement form. And in short, this can be represented as, since all of them are min terms which are summed, summation of min terms, and this is for also the lowest value given by this one. So this is 0 1, so decimal equivalent is 1, and this is 1 0, decimal equivalent is 2, and this is 1 1, decimal equivalent is 3. I can write this expression in short in this way. Next we will define one more term called standard sum, or it is also called as max term. So what is a max term? Sum term is a sum term containing all n variables of the function in either true or implemented form. So it's a sum term containing all the variables. So this is a standard sum term. That means a normal sum term may contain any number of variables. That means if a function depends on 3 variables, a normal sum term may contain all the 3 variables or 2 variables. But a standard sum term or a max term should contain all the n variables of the function on which the function depends. For example, so for a 2 variable function, if I assume that the 2 variables are a comma b, then the max terms will be a bar plus b bar, a bar plus b, or a plus b bar and a plus b. So these are the 4 different max terms that are possible for a 2 variable function. So here these are the sum terms on which contain all the variables. Since the function, we assume that the function depends only on 2 variables, these all 4 sum terms contain only 2 variables. So now these are all the possible combinations of the 2 variables on which the function depends. So that means for 2 variable function we got 4 max terms, 2 4 2. Similarly for a 3 variable function, and here you can see that a variable is present in its original form if its value is 0, right? So if a variable possesses the value 0, if variable possesses the value of 0, then it is present in its complemented form. Uncomplemented form. So now if the variable possesses the value of 1, then it is in its original form. So that means in a standard sum or in a max term, the variable is present in its complement form if its variable value is 1. The variable is present in its true form if its variable value is 0. So, and you can see that we have, based on the standard sum terms or max terms, we have one more way of expressing the boolean functions. It is called as standard product of sums. Standard product of sums. So then what is meant by standard product of sums? So when a boolean function is expressed as the logical product of all the minterms, all the max terms for which the value of function is 0. So when we express a boolean function as logical product of the max terms, which max terms? Max terms for which the value of function is 0, then that form of expressing the logical function is called standard product of sums form. So if I assume that a function f, so for example, if I assume that a function f depends on 3 variables, and if value is 0 for 3 max terms, say a plus b plus c and a plus b bar plus c and a bar plus b plus c bar, then the function can be expressed as logical product of these 3 max terms for which the function is 0. So this I can write in a short way as it's a product of max terms. So max term here represented with capital M, and since it is a product, so I represent it with pi. And next, each max term can be represented by its decimal equivalent for the binary value which it represents. So here the variable is written in its original form when its value is 0. So this represents a binary value 0 0 0. So the decimal equivalent value for this binary is 0, comma, and for this one represents 0 1 0. The decimal equivalent is 2, and this one is 1 0 1. The decimal equivalent is 5. So this expression can be written this way. So this completes the lecture on the representation of the logical functions in standard forms.